And here we go with section 3.2, polynomial functions and their graphs. With me, Mr. Hain. So, when thinking about polynomial functions and their graphs, there's two major thoughts that we want to keep in mind, and I wrote down the first one. The first is, without knowing what function created a graph, a close examination of that graph can tell us a ton about the function. And the converse of this is also true. Without knowing anything about the graph, a close examination of the function will tell us a ton about the graph. And really what the first part means is that with just looking at the graph, given enough examination information from a graph, we can derive the function. Hence my shocked face. Without even knowing anything, we can just derive the function directly from the graph. And the converse of that red statement is also true. Without knowing a lot of, with the close examination of the function can tell us a ton about what the graph looks like before we even put it in a graphing calculator or into Google to graph for us. So let's compare and contrast these graphs at the beginning. A, B, C, and D, the black, green, blue, and purple graphs. So if you want to pause the video and just make a list of all the things that you see that are the same and different between these graphs, I'm going to encourage you to do that. And if you're back from pausing the video, here are some questions that will kind of lead our discussion. So, which of these graphs are smooth? So I see that graph A and B, and to some respect C, are all smooth. They don't have any sharp edges or corners. And unlike we see here with graph D, which does have one sharp corner. And because of that vertex here, we know it is not smooth. So which one of these graphs are continuous? So that would be without a break in the graph. And we see that the only graphs that are continuous are A, B, and D. Now the graphs that are both smooth and continuous are A and B. And again, a continuous example, C has a hole in it, so it's not continuous. So the only ones that, again, that are smooth and continuous are definitely polynomial functions. Here's another question. What is the y value when these graphs cross the x-axis? So I'm going to look at some points here, right here on these 2 points on graph A, right here on graph B when they cross or touch the x-axis, right here on graph C, and D does not touch the x-axis at all. So the y value when it crosses the x-axis is going to be 0. It has to be 0. For the graph to touch the x-axis or cross the x-axis, it's got to be 0. The y value must be 0. So let's take a really close look at graph B. Let's just say this is x equals 3. So I'm going to kind of hover my mouse right here in this area. And you see around the circle that the mouse is making, you'll see that there's kind of like a hump or a bump. That's what we call a relative maximum. And then if we go here to around x equals 0, around where the circle of that graph or the halo of that pointer is pointing, we see that there is a kind of a dip, or what we like to call a relative minimum for graph B. And again, that's kind of focusing in our examination of what happens when there's a hump or a dip in a graph. And we already answered that star question with a dip in graph B. So what would happen if we were to stand at the origin, like right here on graph A, right there, boom, or right here on graph B, boom. What would happen if you could describe, and you were standing at the origin, you were describing just the far ends of the graph, the extremes of the graph. We don't care about the bumps that happen around us, like in graph B, right here. We don't happen to care about relative maximum or minimum. What we care about is the very extreme ends of the graph. Well, if I was looking at graph A and I was standing on the origin, I would see that the graph actually falls to the left and falls to the right. And if I was looking at graph B and standing right here on the origin, I would see that the graph does rise to the left and fall to the right. And that leads us directly into our next discussion about end behavior. End behavior doesn't concern itself with what happens in relative maximum and minimum near the center of the graph or the origin. Really, the end behavior and the leading coefficient test looks at the function ordered from the greatest degree to the least. Really, honestly look at its greatest degree and its coefficient. That's all we have to take a look at for the leading coefficient test, because its greatest degreed term is its leading coefficient. All right, so let's take a look at f and g. I've got some arrows here to help us out. If I look at f and g, they're both polynomial functions. For f, we see the red arrow is pointing to -3, and that coefficient is negative. If we look at the black or dark purple arrow, we see that its degree is even. So that brings us to this chart. Okay, we're going to use this chart to describe end behavior because, again, far enough away, we don't care what happens in the middle near 0. In fact, if we zoom out like a bajillion feet into the air and just look at the very extreme ends of the graph, that's going to give us the information about the end behavior. I'm going to pause. I suggest that you pause the video and write this chart down in your notes if you haven't already printed the notes as well. I'm not going to give you this on a test or a quiz. It's something that you need to know and to have memorized. So back to our function f of x. The negative coefficient and even degree, so the degree is even and the coefficient is negative. That means if I stand right in the middle of this box, the upper left box, I see that it falls to the left and falls to the right. And for g, the coefficient is positive and the degree is odd. So if I look back at the chart, positive coefficient puts us on the right column, and the odd degree puts us at the bottom. So if I stand right in the center of that graph, and it's going to disappear the circle, it falls to the left and rises to the right. So that's what the leading coefficient test tells us, is the extreme end behavior of the graph, not the little stuff at near the origin, but the end behavior. So let's take a look at your turn. We're going to look at several different functions. We're going to look at f. So leading coefficient here is x to the 4th. Leading coefficient is positive. It shouldn't be negative. It's a mistake in the video, but that's okay. We'll roll with that. It has an even degree. Okay, so let's take a look at the chart. This is wrong. We definitely know that the coefficient for x is positive, unlike what's written here. And so I can see that I'm going to have a positive coefficient and even degree, so it rises left and rises right. I'm going to correct these in the downloadable notes. And then for g of x, we see that we're looking at 17x to the 9th. So the leading coefficient is positive and the degree is odd. So if the leading coefficient is positive and the degree is odd, it puts us right here. So it falls to the left and rises to the right. Excellent. And then we're going to take a look at h of x. And so h of x takes us to negative 7x to the 8th power. We see that that leading coefficient is negative. And it has an even degree. So the leading coefficient is negative, puts us in the left column. And an even degree puts us here. So again, if I stand at the center and I look at the extreme ends of that graph, it falls to the left and falls to the right. So let's look at p of x. And we're looking at negative x to the 15th. So the leading coefficient is negative. And that has an odd degree. So looking at the chart, coefficient is negative, puts us in the right column, and an odd degree puts us here at the bottom. So it rises left and falls to the right. Excellent. Rises left and falls to the right. Make sure that if you're writing these down, you correct this. The leading coefficient here for f of x is positive. It is not negative. This is incorrect. It will be corrected on the downloadable version of these notes. So let's take a look at the zeros of polynomial functions. So if it's not factored, the key here is factor. Look back at the first section of these videos if you want an example of factoring. I did attach, and you can search YouTube for the Xbox method for the method that I use. But if it's not factored, then factor. This is extremely important. So let's take a look at checkpoint 4. I've already factored it for you. So we're going to look at just the zeros. So I'm going to use the zero product rule or the zero product principle and square root both sides. So I have x plus 2 is equal to 0. And so x is equal to negative 2 would be what makes the first term 0. Same thing, zero product principle or zero product rule isolates the second factor and x would equal 2. So the zeros of this polynomial function are negative 2 and 2. It's where the graph crosses the x-axis or touches the x-axis. We don't know yet. So let's take a look at a second example, and g of x. So here I have 3 terms, so I'll absolutely have 3 roots at least. using the zero product rule, I set it to 0, and then I'm going to solve each of them to see what would make them 0. The first one is 0. The only number squared that would equal 0 is 0. Second one is -3. If I put -3 into this quantity, it would turn this quantity into 0, which would make the statement true. And the last term would be 3, because if I put +3 into the last term, it would make that last term 0. Excellent. So the zeros are -3, 0, and +3. And this is where the graph crosses or touches and turns the x-axis. We don't know yet. So that, of course, is going to bring us to the multiplicities of 0. So really, multiplicities looks at the degree of a 0 to tell the behavior of a graph at the x-axis of that 0. So let's go back to checkpoint 4. So we're going to look at two different terms. So the degree of the first one, x is -2, is even because this has a 2. So an even degree means that it touches and turns at the x-axis. And don't worry, I'm going to have a visual example of this. And if you look at the second term, x equals 2 makes the second term 0, and it has an odd degree, because if there's nothing there, the degree is 1. So it crosses the x-axis. So using the power of a graphing calculator or Google, we can sketch a graph of the f of x, and we do see that at x equals -2, the graph touches and turns away. I don't care if it's positive or negative, I care that I know that it touches and turns at the x-axis. And then here also I see that at +2, it crosses the x-axis. It goes from negative to positive. So that's what the multiplicities of zeros are going to do for us. They're going to tell us the behavior of the graph at that 0. So again, where it has an even degree, it will touch and turn, and where it has an odd degree, it will cross. So let's take a look at some practice examples. So if we look at the g of x, we have a couple of factors. We have x minus 1 squared and x plus 2. We don't even care about this negative. It doesn't. We don't care about it at all. We do care that if we put +1 into the first term, it would make it a 0. This is a 2. The exponent is 2. So the multiplicity, since the exponent is 2, it has an even multiplicity. I use a M circle for multiplicity. So it touches and turns at the x-axis. And if you look at the second term, x plus 2, if I put -2 in here, it would make that 0. And of course, if there is nothing written, it has an odd multiplicity because its exponent is 1. So the graph crosses the x-axis. So let's take a look at h. If you want to pause the video and see if you can do this one on your own, do that. It's challenging. I did it on purpose. Remember, we're looking at the exponent of the entire term, the factor, not just the exponent of the variable. So if you unpause the video, you see that I have -2 and plus or minus 2, and that's where it comes from the first term for h of x. It's an odd multiplicity because the multiplicity is 1, and it crosses the x-axis at the -√2 and +√2. And at x equals 1, it has an even multiplicity because that's a 2 for an exponent, so it definitely touches and turns at the x-axis. I would take a moment, I would graph h of x in Google or on your graphing calculator to show yourself that this is actually the behavior of the graph at -√2, +√2, and at 1. So here's a final example, p of x, for multiplicities. So I have two multiplicities, or two terms, factors. I've got x equals 0 from the first one. Has an odd multiplicity because the exponent is 3, so it crosses the x-axis at x equals 0. If you look at the second one, the second term, putting a +4 in it will definitely yield us a 0. So it has an even multiplicity, and so it touches and turns the x-axis at the x-axis. We don't know if it touches and turns on the positive side of y, or if it touches and turns on the negative side of y, but we do know that it touches and turns. So again, multiplicities tell us the behavior of the graph at a 0. It does one of two things, either touches and turns, and that's if it has an even multiplicity, it will touch and turn, and it will cross where it has an odd multiplicity. And remember, factor, factor, factor. If it is not factored, you must factor. Cool. Let's take a look at the intermediate value theorem. So this theorem sounds super duper complicated and has a lot of conditions, but when you see it on a graph, it's actually pretty dumb. And I mean dumb as in like easy to understand and kind of quick. We'll go over it so that we can all be on the same page. So if we let f of x be a polynomial function with real coefficients, so f of x has to be a polynomial function, f of a has the opposite sign of f of b, then there is at least one real root c where the f of c is 0. So visually, this makes a lot more sense. So if I have this crazy polynomial function, and my red f of a, it's definitely negative, so its value of the y value is definitely negative, and this f of b, the orange f of b, is definitely positive. The intermediate value theorem says if they have opposite signs, there must be at least one real root c where f of c is equal to 0. In fact, if I look at the graph, I see I have 3. So that is indeed at least one f of c where f of c equals 0. So I'm going to ask you this like this. Checkpoint 7. Show that the function f of x, 3x cubed minus 10x plus 9, has a real 0 between negative 3 and 2. Super simple. We just plug it into our calculators. If f of negative 3 is equal to negative 42, and then I plug in f of 2, and that would equal 5. The sign change shows us there is a 0. There's at least one 0 between negative 3 and 2. I don't know how many. It could be like this. There could be at least 3. There could be a ton of zeros. But we do know that because the sign changes from negative to positive, there is at least one 0. Now, had this 42 been positive, there could be a 0 and there couldn't. We don't know. It might have been. But because one is negative and one is positive, we definitely know that there is at least one 0. All right, because of the sign change. So our final topic is the maximum number of turning points. So the key term here is maximum number. So if I have an x squared function or quadratic function, the maximum number of turning points is 1. It would look kind of like this, like a U. Upside down or right side up, doesn't matter, it would turn once right at this point. If I have a cubic function, or x to the third, like this red graph, you can see I could have a maximum of 2. Sometimes I have 1, but a maximum of 2 turning points. X to the fourth, the orange function here, I could have a maximum of 3 turning points. If you see a pattern, the turning points is just 1 less than the highest degree factor. So if I x to the n, I would have n minus 1 as my maximum number of turning points. So I look at r of x, I see that the leading coefficient is x to the fifth. So 5 is my exponent. That means, you guessed it, maximum turning points is 4, so it's 5 minus 1. But what if I gave you this, t of x, and I left it factored? What would you do? The key here is looking at multiplying. Now when I FOIL, I want to find the highest degree, and that's when I multiply these two. 7x to the fourth times x to the fifth gives me 7x to the ninth. I don't care about the rest of the function if I'm asking a maximum number of turning points question. All I want to know is the degree of the leading coefficient, which in this case would be 9. So if 9 was on this chart and it was x to the ninth, of course the maximum number of turning points would be 8. So there's a lot that we talked about for polynomial functions and their graphs. This is definitely a video you want to rewatch, pause, rewind, compare notes, correct the notes from the video if you did that, and make sure that you understand the different principles about polynomial functions and